Ice tables are popular for calculating the equilibrium constant. So here you set up a table where you have the initial, change, and equilibrium concentration. So for example, you'd be given the initial concentration of the reactants and products, and an equilibrium concentration of one of the products. So therefore you can calculate the change in concentration of product C in this case by subtracting the initial from the equilibrium concentration, and then using the mole ratios we can figure out the change in concentration of the other reactants and product. So for every 2 moles of C that are produced, 1 mole of D is produced. So therefore, half the concentration of C is produced in this case. And 1 mole of B and A are consumed. So we put a minus here. And then you sum all these together. And then you can calculate the equilibrium constant by taking the ratio of the products raised to their stoichiometric coefficients, on the concentrations of the reactants raised to their stoichiometric coefficients. And other problems are straightforward. So for example, you may be given 3 equilibrium concentrations and their equilibrium constant and asked to solve for another concentration. Or you may be given the partial pressures of gases and asked to calculate the equilibrium constant. Or you may be given solids or liquids which you ignore in a calculation of the equilibrium constant. And we'll cover some example problems. 2 moles of reactant A and 3 moles of B are combined in a 2-liter rigid container at 900 Kelvin. At equilibrium, 0.5 moles of C is observed. What is the value of the equilibrium constant for this reaction at this temperature? Well, we can construct an ice table because we know the initial concentrations of the reactants. So we have 1 molar of A and 1.5 molar of B. And before the reaction initiates, we have 0 concentrations for the products. And at equilibrium, 0.5 moles of C is observed. So that'll be 0.5 on 2, which is 0.25 moles per litre. And therefore the change in molar concentration of C is plus 0.25. And for every mole of C that's produced, 2 moles of D are produced. And 2 moles of B are consumed. And 1 mole of A is consumed. And now adding all these together, we obtain the equilibrium concentrations, which we can use to calculate our equilibrium constant. So in the numerator, we have the concentrations of the products raised to their stoichiometric coefficients. And in the denominator, we have the concentrations of the reactants raised to their stoichiometric coefficients, which gives the following result using one significant figure.